Thank you. All right. So infinite dilution, this is equal to the A21 value, and at the natural log of gamma 2 at infinite dilution is equal to the A21 value. All right. Sorry for going back and forth so much. All right. That's the important part about this, because whenever you're solving stuff later, Dr. Griffith's going to give you an example problem for a test probably. I don't know if he has or if he will. I don't know what the plan is, what that is exactly. But if he does, that's going to be helpful, I promise. So that's where this comes from. That this is equal to the gamma 1 value at infinite dilution. And so you can also see that the natural log of gamma 1 is equal to the A21 value. The natural log of gamma 2 is equal to the A21 value. Yeah. All right. And Dr. Griffith also said that we're taking out this data point right here because it is a statistical outlier. And we highlighted our data based off of that regression. I took out the actual regression analysis. I just left the A1221 values. One thing I did want to mention, if we were to take out these two data points as well, it would actually give an even better regression. The R squared for this data ends up being like 0.998, while the other one is 0.9998. So it's not much better, so there's not really much of a point of deleting that data unless you just really feel like it. And there are better ways of determining whether or not something is a statistical outlier based on a lot more statistics than just looking at, oh, that data point looks bad, so I'm going to take it out. No, there's standard deviations that we can do, and honestly, unless you're interested in statistics, you won't, as a chemical engineer, you probably won't have to do that because a computer will do it for you. So it'll just be like, oh, that data point doesn't fit the spec of what we're looking for. So we're gonna throw it out because it's bad data, and the computer would just tell you to do that. It's important to know how to do what we're doing though, because manipulating equations so that we can model things that we're looking for is very important. And so what I'm going to show you now is hopping into that.
Daniel.
Problem. Yeah.
How are you getting your ln gamma 1 and ln gamma 2 values?
Of these? Okay.
Yeah.
So all I'm doing is I'm taking that equation that I wrote earlier right here. So the gamma 1 is equal to the x2 squared A12 plus the 2 times the A12 minus A121, or the other way around. X2. All right, so that's how we get that, and it's right here. So x1 squared times A21 plus 2 times A12 minus A21 times x2. That is what gamma 2 is equal to. All right, and then gamma 1 is the exact same thing. Just flip the where you see a 2, you put a 1, and where you put a 1, you see a 2. Same thing. All right.
When I square it, I don't get those values. I have the same thing now.
You probably made a mistake somewhere. I'll check it. Just send it to me, and I'll take a look at it. But it's not super important as long as you know what the equations are supposed to be. Just check your work and see what you get. I'm gonna go ahead and show y'all how to not regress, but find the temperatures that we're trying to approximate using.
You're recording this, right?
Yeah, I am recording this. Absolutely.
Okay. All right. Thank you.
Definitely. It's definitely yes. This one's recording, yeah. Okay. So we're going to model the temperature and also by eliminating the sum of the squares. And that's going to be used in Solver. So we're going to use a little bit of Solver today, so that'll be fun. So what I'm going to go ahead and show y'all is this process. So we got for, and we need to explain why. So what this is going to do is we're going to assume that the A12 and A21 values remain constant across the PXY diagram, which is basically what we got going on up here, versus the TXY diagram. And that technically isn't true, but it's very close to how it would act. It's not exactly, but it's a good enough fit for us so that I can show you what's going on. And I really do mean good enough. So what we're going to have to do is we're going to have to recalculate and we're doing this for atmospheric pressure. That's important to mention because otherwise we don't have anything to correct it off of. So we're going to assume that we're making a TXY diagram for atmospheric pressure. So what we should expect to see are the boiling points, like right here, where, let's move this out of the way so that way y'all can see. I want to copy and paste this right there. Okay, so what you should expect to see, if this is 100% water, what would be the boiling point of water at atmospheric pressure? You should expect to see 100 right here, roughly. And at the bottom, you should expect to see the boiling point of ethanol, which is about 78.2 or 3, whatever. Doesn't matter. But you should expect to see a range that decreases the temperature that comes down. And that's what we're trying to model. And we need to use the partial pressures in Antoine's equations to model that, and then find the P total calculated, which is just the total pressure. And then we can subtract the error, which is the P total minus the P calc, and then we square that just to make sure that we get an even better fit. Squaring it means that the numbers are a lot bigger. And you don't have to square it. You can find the sum of the errors. It's just you'll have a much better. If you're trying to force something to 0 and you have a big numbers, and then trying to mitigate that, it will end up with a better decimal place fit if you have it squared. And so all this does is manipulates around Antoine's equation and Raoult's law, and we find the the vapor data and the liquid data we already have. So we were trying to find the vapor data that is recalculated after the regression, or after regression, basically. So this is technically like a second regression because we're taking the sum of the squares. It's just a different way to regress data. So I'm going to go ahead and type this out. So what this is Antoine's equation right here. So I'll do the next line. It'll be EXP. Why is it in? All right, cool. We're just going to have it in italics times the A value minus the B value over the T value. For some reason it wants to block it, so plus the C value. I'll make sure that that's right. Yep. Look right to everybody, except I need to make that absolute, except for the temperature. So I can click and drag it down. Just gotta make sure that that's correct. All right, cool. So just so. Yeah, that's right. Okay. Just gave me more decimal points. So I can click and drag that down to the bottom. And what it's doing is it's calculating based off of the temperature. So with 32 or whatever, it'll give me a different pressure. Same thing over here, except we're going to do it for water this time. So exp times the A value minus the B value over the C value plus the temperature. And then we're going to make all those absolute, except for the temperature. Okay. An interesting thing, if you want to just, instead of clicking and dragging it all the way down, you can just hover over this little square. It'll turn into like the little plus sign, and you just click it twice, and it'll drag it down. Mine goes all the way down just because it brings it to the very last cell that it has data in. So if I didn't have the sum of the squares there, this wouldn't have been there. But that's just also nice to know because if you have sometimes in reactors you'll have simulations that go down to the thousandth place, the thousandth cell. It was hard to say. And so you're going to want to do that sometimes instead of having to click all the way down. That would get annoying. Okay, and then right here, we're going to use Raoult's law. The sum of the partial pressures is equal to the total pressure. So this would be x1 times gamma 1. So gamma 1's up here. And we're using gamma calculated because we're using the regression data. Let me make sure that that's true real quick. Come on. Yes. Since we're using the regression data, we're trying to model. So we're going to use the recalculated gammas. So this gamma 1, okay, times the psat 1, okay. So x1 gamma 1 psat 1 plus the x2 times the gamma 2, and that's the wrong thing. That's gamma 1 all times the partial pressure of 2. Okay, so x1 gamma 1 psat 1 plus x2 gamma 2 psat 2. And those are for the calculated gammas that we have recalculated. Okay, and all those aren't going to be absolute just because we're trying to model the regression after the fact for the T. All right, and all this is just the total pressure that we're assuming it to be at, which is in kPa, minus this value squared, okay? We can click and drag that down, and I'll delete this. And lastly,
Can you show that again, Daniel?
the errors.
Yes.
Yeah, okay. So it's going to be, all right, so P total, wherever you write that, you need to put an equal sign. So P total minus P calculated, and that's going to be squared. Okay, and P total needs to be absolute. I'm going to click and drag that down. All right, cool. So now we can, just because I want to get a TXY diagram, we're also going to calculate the Y's. Now, to get a regression, we don't have to use this data isn't needed. We don't need this to get the the temperature distribution. We don't need that for the temperature distribution, but we want it for our graph. So I'm calculating it anyway. Okay, so what this is, I'm making sure that I did that right. Okay, cool. Yeah, so what this is, it's Raoult's law with the activity coefficient rearranged. And so what that is, it's x1 times gamma 1. Yet again, we're going to use this gamma 1, all right, times psat. And this is going to be divided by p total. And in this case, p total is this, because what we're looking at is we're trying to find the temperature at which a system would boil, an ethanol water system would boil given its VLE data. Or given its, actually no, given its liquid data. So we're trying to, basically that's what this models. It models the boiling points of ethanol water system. Just gonna make sure I typed that in right. Yeah, okay, I did. So I guess the last equation that I could write onto this would be Raoult's law, but I know y'all have that, but just so y'all all have it in one spot. So y sub I p total is equal to x sub I gamma sub I p sat sub I. Okay, and so p total is equal to the sum of the y sub I p total, if you have that, which is obvious because the sum of the y's is 1. What's less obvious though is this, the sum of the x sub I sub I p sat sub I. And that's less obvious just because the activity coefficient could be literally anything. And so could psat. We know that the sum of the, I wrote this before, we know that the sum of the y's sub i's is equal to 1, and the sum of the x sub i's is equal to 1. I'll get into that at the end. I have something else to tell you, but I'll mention that at the end. If y'all, sorry, were y'all done copying that? If y'all wanted it, I don't know if y'all wanted it or if you already had it. You probably did. Yeah, okay, figured. So this is just, to finish, this is just 1 minus the y value. Now, you could check your work here and redo it all over again. So you just have x2 times gamma 2 times the psat. You see what I'm doing? Which, in this case, the answer is yes. It should match exactly what you have. So yeah, that's a good check if you wanted to check your work. 1 minus this should equal the other, and that's a proof of what I just wrote down right here. Now, this doesn't look quite so good because if we were to type in the sum of the squares, so we were to sum up these right here, it would not give a good distribution. This is a really bad, this needs to be mitigated to 0. So what we're going to do is we're going to use solver, excuse me, to do that. All right. to show this the best. Okay, I'm going to move this right there. I'm going to scroll this over to the side. All right, cool. So, what we're trying to do is, I don't know if y'all have used Solver before. Have y'all? Or do y'all have it downloaded?
We have it a bit. We have used it a bit in Griffiths.
Okay, good. Okay, I wasn't sure if y'all had it downloaded or not, because that's something that you have to go find. It's not super hard. Oh, you haven't? Okay, Raven, do you have it downloaded? Okay, well, watch this for now, and I'll send you a link on how to do it. Just remind me through an email that you need it. Okay, so just watch it for now. It'll be in your data. Here, I'll start over. It'll be in data. Sorry, I gotta wait. His tag is right there. Okay, so you can go to Solver. This is after you've already downloaded it. It's in the analysis tool pack if you want to go look it up. It's easy. It's pretty easy to install. They have a very good setup for it. Okay, and so I'm going to set my objective to. This is my set objective. Okay, so what I'm trying to do is I'm trying to set this to a value of 0. You could also just say that it's minimizing, since it's basically the exact same thing. In this case, if I wanted to set this to a value of 100, for instance, I could do that. But in this case, we're trying to minimize the sum of the squares. So I'm going to click that cell. Okay, and we're trying to change the temperature value. So I'm just going to change all of the temperature values, all of them at once. Okay, and nothing else I need to add. I would like my temperatures to be non-negative, but it doesn't really matter. But I know that they're not supposed to be. Okay, cool. That's everything. So I'm just going to go ahead and click Solve and see what happens. It should give me a distribution across. There we go. Okay, and so I can run Solver again to make sure that it did it properly. This looks a little wonky. I don't like how that looks. Let me see if that's what happened in my other one. Oh, whoops. It shouldn't be, at least I don't think it should. No, it did do that in my other one. I just missed that. Okay, that's interesting. So the temperature dips down below the boiling point of ethanol at a high ethanol concentration. That's kind of interesting. It drops the boiling point right there. Okay, but I'm going to go ahead and do that again. I'm going to do Solver again because sometimes it doesn't give you the best sum of the squares immediately. If you do it twice, it would give the best result because it has to find, what is it called? Its initial guesses might have been off, not find. So I'm going to run it again and see if it did it. So yeah, it found an even better result. Let's see if it, that was so different. I'm going to see if I can do it a third time. I actually haven't ever gotten it down this far. Okay, cool. Yeah, it's done. So you can do it twice, 3 times, however many times, but this is basically equal to 0. So that gives us the p-calc regression that we were looking for. I got 10 minutes. Okay. So now what I wanted to do was I wanted to show that.
Daniel,
Yeah.
can you go over how you found the P calculated again?
Yeah. So this is the sum of the partial pressures using Raoult's law. This is a manipulation of Raoult's law that we know is true because whenever you write normal, like the normal thing of Raoult's law, we know is this: y sub I p total. This is equal to x sub I p sat sub I. Okay, and so I can just plug this in and know that if I had the sum of the y sub i's, so like let's just say that I'm trying to find what p total is. Okay, and this is equal to the sum of the x sub i's p sat. Okay, p total exists across each thing of y, so I can factor that out. So technically, it starts off like this. Okay, but p total isn't a isn't due to the summation, so I can take it away, where I know that the y sub I is equal to 1. So I'm just left with the p total, okay? So in this case, this equals the sum of the partial pressures, because technically this is a partial pressure. Okay. Using the activity coefficients, though, it's a bit more difficult to understand, and I personally am still confused on how that actually works, because it manipulates these. Well, that's not right. I don't know why I even said that. It still does the same thing. You just add in the activity coefficient. My bad. Simple. So involving the activity coefficient, it's the same thing. It's the same result. Because the sum of the y sub i's is equal to 1. Okay? And so that's all I have typed in right here for that. So it's the x1, gamma 1, psat 1, plus x2, gamma 2, psat 2. Okay. Now I wanted to get a graph of the TXY diagram. So I'm going to go ahead and actually I'm going to highlight this. I'm going to go to Inserts, Chart, and I want this to be not a scatter plot. Okay. Okay. So, wait. Need to select the data. I'm just showing y'all. Y'all don't need to. Y'all will need to make this, but I'm just trying to do it quickly, so y'all see what we got going on. All right. So that's the TX diagram right there, and I'm going to go ahead and add another one, and I'm going to call this the Y, where that's the same for ethanol. The X values is the same for ethanol, and the Y variable is going to be, okay, well, I know that my Y variable is right there. Okay, and so what I'm going to use is my dual axes idea. I think I can, no, not the data point. Oh, cool. There we go. Okay, so last thing. I'm trying to show this. There we go. Okay. So I want that. Oh wait, no, that's good. That's good. This axis is what needs to change. Not that it matters a whole lot. But I want it to be like 50 so it has a better distribution across the, or 60. Across the temperature. Okay, so if I were to draw a line, or not, insert a line. Where are those?
Click on Insert Illustrations and then Shapes.
Yeah,
You'll find it.
Thank you. All right, so we can go a straight line across this, and you can see where the azeotrope is right there, and that's what we should expect. And you can do that for this data right here, the data that Dr. Griffith gave us. We can find the azeotrope. I'm just showing that we can do the same thing for the regress data, because technically these values, this value does not match this value. And yeah, now that's just because this is the regressed data. Okay. Now, it will be y'all's job to make this graph make make the TXY diagram. He also wants a PXY diagram. We're gonna give y'all some data, and I'm gonna show y'all how to do that again if you'll have some questions. And last thing that I would want from y'all. I'm kind of running out of time. I guess I'll pick this back up on Friday about what else like we're gonna do with this. But this is the gist of what we're gonna do, and I'm gonna tell Dr. Griffith what we covered. He'll cover some more of this tomorrow. I'm not sure exactly what he's gonna end up doing. But are there any questions for me in the next few seconds?
Yeah, can you post this relatively sooner than later on your YouTube channel
Definitely.
so I can watch this again? Thank you.
Yeah,
I appreciate that.
I did model some data based on, like, I just wanted to show y'all. I modeled the data earlier, and I got that graph that I showed y'all initially today, and it does model it very well. So that's good to know. Just figured I'd show it to you, that this being the A21 value and this being the A21 value, and you can see a good fit for the Gibbs free energy. That was what was up here. That's all. I just wanted to share that with you. Friday, I'll pick this back up. I'll pick up wherever Dr. Griffith leaves off tomorrow, because we're kind of tag teaming this one. So, all right, cool. That's it. I'm gonna go ahead and stop.